I opened the Q&A session, so please go ahead whenever you have any questions. I try to catch you. If I don't see you, just start talking.
Karan.
I see some clapping hands, and I see Karan. Just go ahead.
Sure. Like my question is, like for a neural network, the number of parameters to train would be independent of the domain size. But like, correct me if I'm wrong. But like it seems for the polynomial surrogate model, like the matrix, like you have to invert or iteratively solve, would depend on the number of the points in your domain, right?
I mean, like in general, they will not depend. As I say, you have one polynomial degree for the polynomial surrogate, and then this polynomial degree determines the cardinality of the parameters that you want to solve, and the other one independent is the point where you compute the integral, and then this is so your training points live. Yeah, they come from this polynomial, from this from this degree. And your parameters comes from this other degree. So now that we observe they perform the best if they are the same, but in general, they don't have to be exactly the same.
And have you tried this for higher dimensional, higher resolution problems?
So as I was saying, until yesterday, I only tried the neural network, so the Sobolev QH PINN approach, so using neural network as surrogate in 3D, and it works good. It works better than just using normal pins. Yeah, so this is the only one with neural networks. With polynomials, not yet, but
okay. And yeah, I suspect domain decomposition would help too, and you're already working on that.
Exactly. To overcome this issue of the number of points.
Okay, yeah. That's a very nice talk. Thank you.
Thank you.
A general question. So you're checking against regular pins. Do you envision this? Do you want to compete with regular spectral solvers? Or I don't know, but it's a question. Would this method also be even faster than spectral methods? You have a similar problem that we have to invert a matrix also in spectral methods, but is it maybe here more advantageous? You have said
in spectral methods you use FFT, which is
so I will say that for let's say the classic spectral method. So this could also be considered as a spectral method in particular. And then we have also found papers in which they do solving this problem. So just inverting this matrix. There is already some literature about that. Now let's say the additional thing that this framework or that this formulation offers is that it in general could be extended to any nonlinear PDE by doing the gradient descent. And so this is the first one. So the possibility of solving nonlinear PDEs, which is what pins promise, right? People say we should go into pins because they can solve nonlinear PDEs compared to classic methods. And the second one is that we have a soft constraint optimization problem. So the boundary conditions are not imposed in a strong sense, but they are imposed in a soft sense as an additional loss. So this gives a lot of flexibility of the method, as with the neural networks. So if we want to solve inverse problem, we can also solve it in this sense. But of course, it's a good question to just benchmark it against just classic spectral methods. And yeah, this is part of the work that is going on right now.
Right. Classic spectral methods are also often highly parallelized. You have not yet parallelized your method, right?
No,
as I understand. But could that be done in principle?
Sure. Yes. And if we apply this domain decomposition, it can also be done.
Yeah, maybe exactly a comment to that. So in principle, it could be seen as a spectral method. Classic spectral methods also, of course, have often specific extra assumptions like periodicity, if you rely on fast Fourier transform spectral methods, or certain other properties of your equation. If you, for instance, look for fast multipole methods, right, they rely on, I have a long distance interaction and a short one, and they have a certain distance between that and things like that. Okay, so this is the first point. The other point is exactly that it's not parallelized yet. So and I mean, so the question of how much things scales and so on. So it seems that, let's say, dimension 3 is doable even still on the laptop. Right, and if you go on to further than that, then you have to start thinking how to parallelize it, how to put it on HPC and things like that. Which is so there's still enough freedom to scale the things up.
I have more questions, but I'll wait.
Yeah. So
Someone else.
someone else has questions, maybe? No?
Can I ask like a really basic question? I mean, like when I solve PDEs a bit like the Poisson equation, right? With some parameter different from beta because it's discrete. But like maybe you mentioned this, how would I choose the values that I solve for in order to interpolate between let's say I have a solution for L equals 0 and I want all the solutions up to L equals 30. How do I then like choose which ones to solve exactly to get the interpolate?
So imagine, for example, there is 1D, so this is your X, and then in theory you will have your 1D solution, right?
Yeah.
Here you will have your boundary condition, then you change the boundary condition, obtain another solution, and then let's say this axis is the parameter beta. So you should choose the Legendre nodes in the direction of beta. So the normal Legendre nodes, they will look something like, they will be a little bit more dense here at the boundary, and then they will be more.
Okay, so it's some theory that gives you this Legendre nodes.
It's a Legendre grid.
Okay.
And then you will sample here, so more toward the boundary, and then here a bit more sparse, and then toward the boundary more. And then you will get data, everything on the Legendre grid, and you just interpolate this 2D surface. Right? And it will be continuous, and it will give you the value of your solution for any value of beta.
Okay.
In the range.
In the range of course, it's important. It's not extrapolated, it's interpolated. So I don't know. We did it from 1 to 20, I think. In this case, that's not 20.
I think maybe exactly to the question, do you want to compete with spectral methods? Maybe not, but what I mean, of course, the things is we want from PINNs or from such approaches is to have surrogate models over a range of parameters or inferring parameters in a particular range or things like that. And then incorporating this directly in the scheme with the losses can be analogously done as for the PINN approaches, but seems to reach better accuracy and faster performance.
Okay, let me ask you, I want to ask about this. So you showed this here, and let me ask, let me forward the question that Karan received at the APS March meeting.
Okay.
For the harmonic oscillator.
Yeah.
The question was in the harmonic oscillator case. In your case, you're looking at the eigenvalue problem. So you're looking at, I think, lambda, the state 31 or 21, right?
But this is for Poisson, but
no, I mean the
quantum harmonic.
The quantum harmonic oscillator. 21. So what? So here, there's a. If you look at the eigenvalue problem, there's you can pick a parameter in the problem, this frequency or the curvature of this parabola of the harmonic oscillator. And it's basically scales linearly with these eigenvalues. So if you change this parameter, all the eigenvalues change linearly. And I was curious, did you check here what happens? And do you, so like the beta in the previous problem, did you check here for this omega parameter?
No, not yet. But yeah, but it's something that could be easily extended. I mean, taking the CPU time just.
That would be interesting to see if it has this very simple relationship. It's just a linear dependence.
And then see.
As you scale omega, these eigenvalues scale up and down. And PINNs cannot. I mean, what we have seen is PINNs have trouble getting this accurately.
Okay, so doing the same with the transition for the 1D Poisson with the beta, here doing with the omega for the QHO.
Exactly, and if you
give you a good surrogate model for all the range of whatever.
Exactly, if that works, I mean, if it worked for the previous model, probably it will work here.
Yes.
Then can show something that didn't work as well for the pins. But correct me, Karan, if I'm wrong.
Yeah, but I also wanted to say that in the time-dependent problem, like the relationship between omega and the solution is not linear. And like I had some success getting it to transfer over across different values of omega. But like with pins, it's not very clear how to get the fixed eigenvalue for an eigenvalue problem, like the time independent case.
Maybe a more general question, like based on this example, how far again can you go in terms of lambda, in terms of the state, do you think? Can you go up?
So far we have reached 31 with this one example. And maybe Phil, do you know if we have reached higher eigenfunctions?
The thing is, since now the way we compute the eigenfunctions, so when you take more than 31, you get an error because the numbers get too high. So when computing the ground truth. So, but I mean, in general, for the PDE formulation, we could put it there. But since now we've just implementation of the ground truth, which is, which just can reach 31. So because you have some exponents there.
But it's due to the analytic control of the ground truth for higher modes. So you cannot compute.
So
lacks in numerical precision, and then it makes no sense to compare anymore.
No, the thing is the numbers get too high, so you get an overflow for the so because you have some exponents you have to some very big exponents you have to calculate and so on. So at least with
it gets too high.
the polynomials are this e to the and then.
But you could rescale it, right? You could
Yeah, that's what I was going to say. Okay. Even with the normalization, it scales.
What do you mean?
I mean that there is a term that normalizes or that scales down each eigenfunction, let's say. Well, I mean, yeah.
Yeah, but I mean, for our implementation, we just had like the 31 example since now. But I mean, this is one which was not done by the pins. So I mean, they couldn't reach lambda equals 31. So we took this as an example. Yeah.
So the 31 it can reach, but it cannot reach is this, because so the big problem in the eigenvalue, in the eigenvalue problem, let's say, or the big issue is how to impose to which solution you converge. And then what I have seen is that it mainly inherits, let's say, the information from the boundary. Now, these solutions are decaying as soon as you start making the domain bigger and bigger and bigger. So less information will be transmitted from the boundary into the solution over the domain.
So sorry. So it was 25. So 51, which was the highest I tested. So because so 25 per.
25 per one.
Yeah, actually, how do you control which? So is it the same polynomial that gives you different solutions for different states, or is it always a different one?
No, it's a different surrogate, let's say, for each.
How do you make it?
Then you
produce a certain state.
It's very difficult problem, you know. And I mean here we more or less cheat, and we don't allow the domain to be that big. So we can still inherit information from here about the number of modes. But if you go away, the order of magnitude of the boundary is too small compared to the oscillations in the center, then it will reach another kind of solution or just pretty bad solution. So yeah, I mean the word bosonet here is very critical. And I have also observed that if you put the wrong eigenvalue into the PDE loss, but the correct boundary condition, then you can still recover the solution. So
but you could probably formulate some loss in terms of the nodes.
This will be some new in the topology or yeah.
But I mean, did I get the question right? I mean, the question is, of course, do you know the eigenvalue, or do you have the hard problem where you say, I find an eigenvalue for that? This is not what's done. It's really known. I know it's 21. Please find the solution. I know it's 31. Find the solution.
Okay, got it.
It's not solving eigenvalue problems.
It's not, but I have this PDE, give me the eigenfunction for the spectrum from 0 to 100. That's not.
But anyways, what Atlas says is very important because here we have convergence problem if the boundary is not, not if it doesn't bring enough information.
Yeah.
Then you can converge to another eigenvalue. So actually, it's very interesting to think on a way on regularizing to which. So
is the problem still well posed if the boundary conditions are not?
Not really.
Yeah.
So, but I mean, what it shows, I mean, this is also what we briefly discussed in right, is that these quantum harmonic oscillators need well-posed boundary problems or are sensitive to little changes there. And it seems that this method is better realizing these things. So right. So I mean, usually sometimes you could say because the difference between the eigenvalue functions on the boundary is smaller and smaller and smaller, then it tends to solve the problem by choosing the wrong eigenvalue mode.
Exactly. If you choose Dirichlet, but if you choose just periodic, then it's even worse. It's even worse on how to regularize.
I mean, these problems, of course, all have limits, but it seems to be much extended now. And,
yeah, we have also observed similar things. Like if we don't have enough information on the boundaries, then it just converges to ground state in the time-dependent case.
Exactly. And now to prevent that,
and this is actually what you see when using just normal pins that suffer from this loss imbalance, and they will converge to. So in the boundary you could see some modes forming, but in the center will converge to zero just to achieve that solution. So it's not but that's why it's very difficult to solve this eigenvalue problem actually.
And it's more difficult than the time-dependent problem, I think, because in the time-dependent problem you provide an initial state, right? So you
regularize.
Yeah.
Which topology it has.
Okay. Yeah.
But yeah, it would be good way to count.
Okay, guys. Some of the audience already has left. If there are no more questions, I would close the talk here, and of course invite to continue discussion whenever you are here or around. Or just write to Juan if you have any demand on extending that. And then I would say thanks you all for attending. We thank Juan again.